UniSA. She was previously the project manager for Mars site selection for the Canadian Space Agency and a researcher at the Centre for Planetary Science and Exploration at the University of Western Ontario. There's a great interview with her on our website, so check that out. But today she's speaking about using machine learning to find water on Mars. Do you want to use
Hi everyone, thank you for having me. Alright, so I'm a planetary and space scientist and I'm a research fellow at the Computational Learning Systems Laboratory at UniSA. So my background is in physics and astronomy, but I collaborate with colleagues who have expertise in machine learning. And one of those colleagues is Associate Professor Mark McDonald, who's the lead of the CLS lab. So on behalf of Mark, I'll give you a quick introduction into what the lab is and the work that we do there. So the primary work at the lab is to do research into machine learning, but the specialization is really to work at the intersection between software, hardware, and mathematical modeling of learning neurobiology. So because of that cross-disciplinary specialization, the lab works with a range of collaborators from different scientific disciplines, from health sciences through to remote sensing, where I work. And really the focus is to work with partners in industry and to make deep learning real and useful for real-world applications. And these are just some of the recent industry partners with the CLS lab. I'm employed on a project with Concilium Technology. It's a really exciting project where we're doing viticulture from space. But what I'm going to talk to you about today is a different project, a side project that's spun out of some of that work. And that is on using machine learning and neural networks to identify some pretty cool features on Mars, and also how can they help us more broadly in as we go forth and explore more planetary environments. So for those of you who are a bit new to Mars, I thought I'd give you a bit of an introduction into where humanity has actually sent rovers and landers to the Martian surface. So some of you might remember the Viking program in the late 70s. So this is where Viking 1 landed, Viking 2 landed over there. Then we had the Pathfinder lander and Sojourner rover, so kind of near to the Viking 1 landing site. Then the Mars Exploration Rover program, so Spirit and her twin sister Opportunity, who we're still waiting to hear from after the global dust storms, but fingers crossed. Phoenix lander, my personal favourite, in the northern Martian Arctic. And the Mars Science Laboratory, Curiosity, who's currently a field geologist on Mars and doing some really amazing work. And then the latest member of the surface family was the InSight lander that landed last week. So what those things had in common was that they were all pretty close to the equator and all in the northern hemisphere of Mars. But our story is going to begin near the southern pole of Mars. So this is where we're working. We're using neural networks to try and detect and segment some fans and blotches in this southern polar terrain around the polar cap of Mars. And these features appear in the springtime. So what are fans and blotches? Well, this is an artist's conception of what's actually happening on the surface to create these features. So I'll give you a bit of a description of what's happening. But you have to imagine, if you can, a process that doesn't occur anywhere on the Earth. This is a totally alien physical process. So what we have at the Martian South Pole is CO2 ice, so dry ice, and meters thick deposits, and it's nearly transparent. So in the Martian springtime, when the sun finally starts to come up over the horizon again, the sunlight passes through the ice and it starts to warm up the materials at the bottom, so dark dust and sand. And because they're warming up, they start to melt the base of that CO2 ice, and it actually sublimates, it releases CO2 gas. And the pressure of that gas builds up and it has to find a way to escape, so it finds fractures and faults in the ice until it's released explosively as these jets. And the jets carry with them all that dust and sand and dark material that they picked up, and it's deposited back down on the surface. And we can see a lovely dark material on the bright ice. And if you have a strong wind on the day, then it's going to be transported horizontally for a little bit. So what we end up seeing when we look at these with our high-resolution satellite cameras is features that look like this. So here are some of those fan shapes. So you've got a few point sources, and you can see the wind went in a few different directions. So you've got some different directions of fans. Here are some nice, thin, narrow fans. Here you can see that the jets were coming out of these particular linear fractures in the ice. Here we have some really nice, they're called spider channels or areniforms, but basically these radial linear networks of fractures. So we see a relationship between where the jets come out and where we have these radial patterns. There's some more little spiders. And here we have one where you can see the wind directions changed over time. A whole bunch of them are going in that way, and then a whole bunch of them are going up that way. So why are we looking at these things? What are we trying to achieve? Well, firstly, we want to try and find them and delineate the boundary of where the fans and blotches are using machine learning methodologies. And this is kind of a way of testing the utility of these methodologies in a different context. And in future, there's lots of other areas where we might want to apply these on Mars and on other planets. But the purpose of this detection in this application is to then derive a geometric description of the shapes. So if they're a fan, what is the angle of the fan? How long is the fan? Because this is what we need to do some important science with these features. So what are our science goals? Firstly, understand where these features are and how their density changes year to year. That's telling us about Martian climate change, essentially. And really, it's to derive the wind pattern from these features. So in case you don't believe me, there are winds on Mars. Here's a little snapshots taken by the Spirit rover. So these are dust devils that go really high up in the atmosphere. And of course, there's a relationship between your local wind pattern and your global wind. So this is the global dust storm from earlier this year on Mars, or the PEAD, Planet Encircling Dust Event. So an image taken in May, you can see a whole range of different features on the surface, but by July, most of that was totally obscured by dust. You can see the top of Olympus Mons because it pokes through the atmosphere, but pretty much everything else we can't see it. And that's a major problem for all the solar-powered rovers on the surface, and it will be a problem for when we have a human presence on the surface as well. So we need to really understand this wind. And there's other science goals too. Although we're looking at the surface, we're learning about a phenomenon that has a deep subsurface dimension. And recent results published this year found that there's a liquid water briny lake underneath these southern polar ice deposits, very analogous to Lake Vostok in Antarctica. So by learning about these deposits on the surface, we're learning about the thickness of that CO2 ice. So what are our methods? We're using a deep convolutional neural network, and these sorts of things perform really well for image classification and object detection tasks like this. And kind of analogous to this cat-dog image that I've got there, we're looking to detect these two different classes, fans and blotches, and to outline them and differentiate them from the background of the image. But what I'm going to show you is just our earliest results, our initial results that we got, where we were just looking at a binary classification scheme. So is there a feature present in this image, or is there not a feature? So in order to do this kind of machine learning, you need large amounts of training data. And so this project has been made possible by our collaboration with the Planet 4 Terrains team. So they've been running an online citizen science project through the Zooniverse platform that you might have heard on. They have heaps of different citizen science projects there. And on this one, they're getting the general public to hand label these high-resolution satellite images and to actually draw out where there's a blotch or where there's a fan and to draw a shape around it. And so we're using that labeled data to train the network for testing and validating the model as well. So this is an example of some of the data that's generated by the users of the platform. So you can see where they've drawn out this ice cream cone around some of the fans or ellipses over the blotches. So just a quick glimpse of some of our earliest results. So in the background here you have a context image from a different satellite camera, but that just shows you the undulating kind of dunes around the southern pole and how you get really high density clusters of these features in some areas. And then that middle strip is image. So it's going to kind of zoom up. So the pink shapes are the output of the algorithm, so where it's detected a feature. And it's done a really good job. It's detected features over a whole range of scales, from those that are just a few pixels to much larger ones. I might go through it again because it's going a bit quick. But you can also see it's done a really good job at differentiating some of the features from just dark areas of the background to really dark areas of dunes. And it hasn't gotten them confused with other spider features or those radial channels that we see associated with them. So some of the next steps are to address the challenge of those overlapping fans and blotches, so to make it add an additional class distinction into the problem. But I wanted to quickly touch on how I see AI being really useful for our exploration of Mars and the Moon and of other planets. So I put a few quotes here that I quite liked. So AI can be useful to provide a collaborator with the scientist, allowing the scientist to focus on analysing and interpreting the data, while robotic explorers search out features of interest. But also AI is an observational tool that allows us to study science that we couldn't get otherwise. So I thought I'd give a few specific applications of where I can see this being useful. So one application would be in detecting small-scale change. So something that we see in areas of Mars that we've been able to repeat image over periods of time is we can see things like new meteorite impacts forming new impact craters on the surface. So we really want to understand what is the rate at which meteors are getting through and impacting with the surface on Mars. And that's going to be really important for us to have well constrained if we're going to send humans to Mars. And that's something that the InSight lander is actually going to be looking at very shortly. But there's other things that change too. We see new channels form on Mars, presumably from liquid water flowing across the surface. And we want to know about water for in situ resource utilization for a human presence. So there's a huge wealth of high resolution satellite data. It would be very useful to utilize AI to detect those changes. But another area is in science autonomy. There's going to be many places on Mars, for example, where we're not going to be able to send people and where we can't send our rovers. So these are some features called skylights, essentially collapsed portions of lava tubes, and that's a Boeing 747 to scale there. So these are areas that we'll be looking at in the future, hopefully sending a UAV to explore, and that's something that will be tested on the Mars 2020 mission. They're going to have a little short UAV flight. So if we're sending a UAV into an environment such as this, then it needs to be able to do science autonomously. It needs to know what to image and what scientific data to gather. And in fact, some autonomous science is already being done by the Curiosity rover, so the Aegis software package that was uploaded to Curiosity, I think last year or the year before, is doing a really good job now at targeting their laser shooting rock instrument, the ChemCam, and when the science team are busy or when they're sleeping, this autonomously detects the targets within Curiosity's field of view and also prioritizes, so green is a high priority target for Curiosity. And really just more broadly, finding targets and prioritizing our data collection. And I see a big role for this when we look at human landing site selection for Mars, for the Moon, and beyond. So we have really well established criteria in what we need for a robotic landing site on Mars, but we have a lot of work to do when we look at what do we actually need to select a site for humans on Mars. In particular, because we need in situ resource utilization for humans. We want water to be there. We need a really good understanding of the quantities and concentrations of water. And we have a large wealth of complex, multivariate, multispectral data available for Mars that we really need to data mine to answer some of these questions. So if you're interested in any of the things that I've spoken about or in any of the work at the CLS lab, then please don't hesitate to get in touch with Mark McDonald or myself. Thank you.
Jordan. Oh, you're right. Adam? Yep, that's right, yeah, sorry. So, Dr. Adam